I'm Jeremiah. I am the co-founder and CEO at Subspace Labs. My co-founder Nazar is here as well. He's our CTO. Tonight we're going to give you a technical overview of the Subspace network. Okay, so to start out, sorry, I'm just trying to get my screen sharing working here. There we go. Okay, to start out, the agenda for tonight is really going to be broken into three parts. We are going to first provide some background and motivation on why we're building the Subspace network, kind of what problems it's solving. We're then going to focus more deeply on how it actually works. We're going to break it down into the three main layers of our stack or our technical architecture. So starting with the consensus layer of how do we agree on the ordering of transactions, and then the compute layer, the execution layer, how do we agree on the outcome or the state of the blockchain when these transactions are executed, and then the storage layer, how do we make sure that this data is actually stored, that it's actually available permanently. And then after that, we're going to talk more about the application layer or the kinds of applications that we are building and can be built on Subspace, and we're going to give a particular focus of Ethereum there. Throughout the presentation, I'm going to take breaks between these sections. I'd love to get your questions if things don't make sense. And please feel free to raise your hand, stop me, jump in if you have a question, if something doesn't really make sense or you need me to go through it a little bit more. All right, so the background here, kind of the starting point is Nakamoto consensus. This new idea of how do we come to consensus? How do we come to agreement on some set of data? Specifically here, of course, it's in the context of a blockchain, and this original idea of proof of work, which was just so interesting because it was a way to actually try to democratize some sort of governance or some sort of agreement over something using computation, which was really sort of a really novel idea at the time. The idea of one CPU, one vote. Now in practice, this did not work out. We quickly got one GPU, one vote, then one ASIC, one vote, and then we got centralization under mining pools, and we have this huge electricity cost for proof of work mining, albeit with a very high degree of security. And so this has led to other approaches. So Ethereum, of course, started under the proof of work model, trying to be more GPU friendly, so more focused on somebody with their own computer, running it in their home, trying to democratize and decentralize control of the network. There's been a limited degree of ASIC. It hasn't maybe been as ASIC resistant as was originally hoped, but did pretty well, I would say. And now is making this transition to proof of stake, which is almost complete with the merge. Proof of stake resolves this energy efficiency, this electricity waste problem of proof of work, but it introduces new problems and new challenges. It doesn't have quite the same security model as proof of work, and it introduces this challenge of concentration of wealth instead of concentration of the power over the network through the mining resources. Now it's over the staking resources and the wealth, and sort of the continued concentration of that wealth over time. Maybe Ethereum's a little bit different. It's one of these very special cases where it started as proof of work and is migrating to proof of stake versus some of the newer protocols, which are just proof of stake from the beginning. They have slightly different tokenomics and dynamics, but it's still a concern. There is this third flavor of Nakamoto consensus protocols, which we refer to as proof of capacity, which is instead of compute or instead of wealth, it's disk space, it's storage, which you're using as your voting power in the network. And this seems to kind of combine the best of both worlds. We get this sort of permissionless, anybody can join the network with their home computer model of Bitcoin or the original goals of Bitcoin, but we have the energy efficiency of something like proof of stake. And that's sort of the vision. Again, the reality has been different. There's been a lot of issues, a lot of challenges with these protocols. And there's one in particular that we're really interested in, that we've been concerned about. Sorry, my keyboard just doesn't seem to want to work tonight. There we go. All right. So just as a little bit of background, to really understand the problems with proof of capacity consensus, or the challenges of proof of capacity consensus, it's important to understand that whenever you operate a node, when you participate as a node operator, a farmer, or a miner in these networks, that there are some resources required to do this. And depending on the type of node you run, there's going to be different resource requirements. There's also different security expectations or security guarantees that you get, and there are different benefits that you provide to the network. So in something like Bitcoin, the default is to run an archival node because you only have to pledge a few hundred gigabytes of space, and you can share, the history. Anybody can sync from you, get the state, so you can verify the new blocks as they come in. If you want to run a full node like in Ethereum, that's going to be a lot heavier to run an archival node in Ethereum. But if you just wanted to run like a full node, well, you can at least be assured that you're on the longest chain and that all the state is correct. But if you want to run a really lightweight client, you can run a light node or a light client, and you're going to have a different security model. You just know that you're on the chain that has the most work or the most stake, but you don't necessarily know if it is the correct chain. And it changes this whole assumption of a 51% honest majority. What can be done if you have a dishonest majority? So with that background, there is this very specific incentive challenge in proof of capacity protocols, any proof of capacity protocol. So that could be Chia, Space Mesh, Filecoin, Burst, Subspace, of course, this applies to as well, of what we call the farmer's dilemma. Okay, so the farmer is the consensus node. It's like a miner in proof of work. And the challenge is that the farmer really has this fundamental choice that they have to make. So they can be, if you're an honest node, you should be doing all this stuff, but there's a cost for doing this. The cost is you have to provide the storage resources to actually maintain the state and to maintain the history on your local node. And so if you have a disk of say 1 terabyte, there's only so much space that you have left over to actually pledge to the plot, which determines your rewards. It's proportional to the amount of space you pledge. And so the natural incentive is to maximize the plot, make the plot as big as possible, ideally all or like as much of your actual available hard drive space as possible, and not store the history, not maintain the state, not verify new transactions, basically run as a light client. And when you do this, what in practice most people do is they just join a farming pool. So we're basically right back to the problem of mining pools and centralization that we had in Bitcoin, or that we got to in Bitcoin within a few years, but we're doing it within a few months in these protocols. So we actually get there faster, and that's because there's this penalty for being a good node on the network, or for being a node that can verify the transactions. And so this is a really big problem. Basically, if we want to have open participation and energy efficiency, then we have to sacrifice security. We have to sacrifice decentralization. And this is sort of the challenge that we were facing, and that we were able to get a grant from the National Science Foundation to work on this problem. Spent quite a bit of time looking at it and trying to come up with a solution. Like, can we figure out a way to sort of have an incentive compatible proof of capacity protocol, which maintains the security guarantees, maintains the decentralization, sort of get the best of both worlds here. Okay, so the solution here is Subspace. This is the protocol. This is the white paper. And there's really 3 key ideas here, which go to these 3 layers of the stack. The consensus layer, which proof of archival storage. So how do we incentivize storage of the history? We make that the thing that you have to prove that you're doing in order to produce blocks. How do we maintain the state? Well, we have a separate class of nodes that maintain the state called executors. So this is decoupled execution. We'll talk more about that later. And then we actually are able to construct a distributed storage or a useful storage network out of this protocol, and make it really interesting and useful for other projects, other protocols as well. Okay, so just to say a little bit about where we're at now before we dive into the technology. So we actually we have a live test network today. We have over 25,000 volunteer nodes on the test network. So this is a non-incentivized test network. We just recently ran a stress test. There were some very small rewards that are going to be given out for that. But we are getting ready to launch an incentivized test net soon, where there will be rewards proportional to the storage that you pledge to the network. We had such great participation in this network that we actually had to create our own telemetry server. We were running it on a sort of shared telemetry server with everybody else in the Summit ecosystem, because we're a substrate-based chain. But they cap it at 1,000 nodes. So we actually had more nodes, it looked like, than basically all of the other parachains and relay chains of the whole Dot-Sama network combined on our test network. And these are all incentivized networks, and ours is voluntary. So it kind of makes you wonder, how many will it be when it's an incentivized network? And then, okay, what is this space? What is this storage being used for? Right now, it's being used to actually archive and store the history of the Polkadot and the Kusama ecosystems. So basically the relay chain, all the parachains, which is 44 chains right now, are actively being archived block by block on our network, stored on our network in this distributed network. And we're getting ready to do this for Ethereum. We've actually already started some of the work on this, and we're going to be eventually doing this for every blockchain in existence. That's really our long-term vision and roadmap, and to kind of have this common infrastructure layer, this archival storage layer for the network, and we can build interesting things on top of that. We can build bridges, we can build APIs, indexing services, and that's just one of the many things that we want to build on top of the Subspace network in the long term. All right, I'm going to take a pause there for any questions, or Nazar, if you'd like to add anything before I move on. Okay, any questions from the group?
This is Chris. I have a quick question. Maybe you'll be getting into it here in the consensus layer, but I was just curious if you could. Like the if you could compare to like IPFS plus Filecoin. I'm slightly fuzzy about what is going on with like the storage model, or the how people are incentivized to store, and how it's I guess you got it baked right into the consensus layer. So anyway, maybe this is going to come right here in your next section.
Yeah, we will cover Filecoin in a little bit. IPFS is really better thought of as a cache. It's not incentivized. It's just sort of a discovery layer. It assumes that there's some sort of persistence layer below it. So Filecoin can serve as that persistence layer. Arweave can. Any distributed storage network, Subspace can. So really, Subspace and IPFS are compatible and complementary in that respect. And we're actually working on an integration with IPFS for that respect. We actually use the same addressing scheme as IPFS does, the content addressing scheme. In terms of Filecoin, the main difference is Filecoin is for temporary storage, or for permanent storage. So Filecoin, you pay by the month, by the quarter, recurring fees. If you stop paying, your data gets deleted, or nodes stop holding it. In our case, you pay once, the data is stored forever, just same as it is when you write something into the call data of Ethereum or OP return of Bitcoin.
Oh, is that a good thing or bad thing?
Well, it depends on the use case, really. And so we're really targeting these use cases where permanent storage is what you want.
Okay, hopefully also, your white paper also seemed to talk about you having a proof of stake part of the consensus. If I was trying to figure out if there was or was not a proof of stake part of your consensus. So
there is. Anyway. It's actually it's part of the liveness of our protocol. So it's more part of the execution side. But I'm going to talk about that when we get to the compute layer, which will be a little bit further on. But yeah, that is part of the talk.
Okay, great.
Okay, great questions, Chris. Any other questions from the group? Okay, moving on. All right, so now we're going to talk about the consensus layer, proof of archival storage. And specifically, the problem this is solving is how do we agree on the ordering of transactions? So going back to the original idea for Bitcoin, it was basically a timestamp server. That's what we're trying to achieve here, just an ordering over transactions. Okay, so the solution here is something we call proof of archival storage, proof that you are storing the history or being sort of like an archival node of the network. In a blockchain, we have some blocks. We take all the blocks in the history since Genesis, and we compile those. We have some database of blocks. So this is sort of the beginnings of an archival node. So this is what every archival node or really full node on Bitcoin already does. The difference is that we say, okay, when you store the history, we're going to store it in a unique replicated, provably replicated form. And this is our setup phase. So this is plotting. Once all the nodes on the network have created their unique replicas, or once any node has created a unique replica, it can join the consensus phase, which is the audit phase, or the challenge response phase of the protocol. And this is how we produce new blocks. So this is kind of a high level, and I'll dive into the individual components. So the first part is the plotting phase. So we take the blockchain history, we actually slice it up. We have a special way that we put it into these pieces, these constant size pieces of the history. We encode those using an algorithm called sloth. Sloth is really just, you can think of it like a pseudorandom permutation, something like AES. We're not using it to get any kind of privacy or secrecy out of the data. It's a public encoding key. We are just trying to make it basically transform it into something that's indistinguishable from random data. So that's the encoding. So the encodings look random, and that's so that they can be part of this proof of storage protocol. We have to do that. And sloth just makes it so that when we decode it, it's about 1,000 times more energy efficient to decode it. So if we're decoding this across 1 million nodes on the network for every single block, we want to use as little energy as possible. So we do these encodings. You can think of this like the blockchain history just being chunked into lots of pieces. And for every encoding that we create, we're going to hash the encoding, which is create a commitment to the encoding, a tag, and we're going to store that in a binary search tree, and then we're going to write the encoding to disk. And then once we're done with this, once we've written all of our available space, we're ready to start in the consensus protocol, which we call farming. So we have a challenge. You can think of it similar to a proof of stake network, like Ouroboros-Praus or Babe, or the way that it works on Ethereum, on the beacon chain, where we have a clock for every slot of time. We send a challenge. The challenge is derives from some randomness beacon, which really exists on chain itself. And each one of these challenges is just a query to this binary search tree. So this binary search tree is a tool that allows us to do very efficient audits. So we're very low overhead, very low compute overhead on the nodes, on the network, on the farmers. And the way you can think about this audit is these tags, these are just hashes, right? And you can think of it like a domain, or sorry, a ring, which is the domain of a hash function. And all of the different encodings on the network are basically just random points on this ring. So you should get this very like uniform distribution over the whole ring. And then every challenge, every time we play this game with the lottery, we have some point on the ring which we're selecting at random. And then we're trying to find, we're doing a search for the closest tag across the entire network, or not the closest, but rather the closest tags. And then there's some particular very small sector of the ring, which is where the valid solutions come from. So this is like a work difficulty. In Bitcoin or in proof of work, we call it a dynamic solution range. And the idea is that as there's more space on the network, that this range gets smaller and smaller and smaller, so that we only get about one block, one proof every 6 seconds. And then if the space were to go down, it would get wider and wider, and this adjusts automatically on chain. Once we find the valid solution, then we can generate a proof of replication. And this is what we're going to broadcast to the network to show everybody that we did actually create this, that we are the valid sort of leader for this round. And the proof of replication consists of the tag, the encoding, which we need to read from disk. We're going to sign them using the same key we use to create the plot. So there's like a cryptographic linkage between the plot, and the identity who's generating this proof. And we're going to broadcast that. And then if anybody wants to validate this, they just decode the encoding. The encoding actually contains a witness, so like a Merkle proof. The piece contains a Merkle proof that we can verify this was actually part of the blockchain history. So that's really the difference between a proof of space and a proof of storage, is we're trying to say not only did this farmer dedicate storage to the network, but they're actually storing the history of the blockchain versus just some random data like on Chia, for example. And then if all that checks out, then we have a valid proof of archival storage, and we can build a new block. Okay, so going back to your question, Chris, about how this is different from some other protocols, at least at a consensus level, because there's sort of multiple avenues of this, but from a consensus level, there's really two broad flavors of proof of capacity. there are, on the left side, we have the useless storage, the random data, or the wasting space intentionally. So Chia wastes space the same way that Bitcoin wastes electricity intentionally. And then you have something like Filecoin on the right side, where it's useful data. It's a proof of storage. In Filecoin's case, they're taking just any arbitrary user data. In our case, we're storing the history of the blockchain as the kind of useful data. It turns out we can figure out a way to make that useful data, because you can just basically wrap it in a transaction if you want to, and get it embedded into the chain sort of indirectly. And so that's one distinction. On the other side, we have this distinction between the is it permissionless, is it permissioned? So permissionless, think of it like Bitcoin mining. Like anybody can just download the software and start mining. They can produce a block. They don't need to register or do anything like that. They can disappear. They can never come back. They're not slashed if they're not active or anything. In a proof of stake protocol, however, you have to have some coins. You have to register. You have to be online. It's a very different kind of dynamic of participating in consensus, and we want to be more like the Bitcoin model. We want to be what's called dynamic availability. Okay, so now let's talk about the compute layer, or the execution layer, and basically this is the question of how do we come to consensus on what the state is after we have agreed on the order of transactions. And the basic idea here is something which we call decoupled execution. And this is basically trying to have a separation of concerns between consensus and computation. So in pretty much all blockchains, and especially Ethereum, it's expected that a full node will do many different things. It will propose blocks, verify transactions, it will maintain the history, and it will also maintain the state. And in short, what we do is we separate these roles between two different types of nodes. We have one type of node who is responsible for the safety of the chain. So that's the farmers. And they're going to use one type of consensus, which is proof of archival storage, or disk-based consensus. And we have a second type of node called the executor. And the executor is going to be responsible for the liveness of the chain. So basically transaction production, or transaction batching in our case, and also the validity of the chain, or basically agreeing on what the global state root is. And all right, there we go. Okay, and how is this secure? How does it actually work? So if we have the blocks which are produced by farmers, again, the farmers are just treating the data, the transactions as this opaque data. They're not actually trying to understand or sort of read what these transactions do. They're just data to them. The executors are going to read these blocks. They're going to know how to interpret these transactions, and they're going to apply them to the state because they are maintaining the state as well. Whenever they complete this execution, they'll generate what's called an execution receipt, which is really just a commitment to the new state root. And then they're going to run an election over that. So they're going to run a proof of stake election, like a VRF election, proportional to the amount of stake that they've deposited in this contract, effectively. For each block, there's going to be a small constant number of these execution receipts, which are going to get elected, and they're going to get gossiped to the network. They're going to go out to the farmers. The farmers are going to treat them as transactions. Farmers are optimistic, so they're going to basically trust or believe that these execution receipts are correct, because the executors, that they're rational and that they want to retain their deposit. And then if an executor produces an invalid ER, all of the other executors on the network all the honest executors will see this, immediately recognize it. Any full node as well will immediately recognize it, because this execution is deterministic. So on the left side, what the farmers are doing with the block production, this is a probabilistic process, right? This is why we have to have a consensus protocol in the first place. In the right side, what the executors are doing is fully deterministic, right? This 2 + 2 always equals 4. So if somebody says 5, well, we know they're committing fraud, and we can generate these succinct fraud proofs that are non-interactive. These fraud proofs can be gossiped to the network. They're deterministic as well. So for every invalid execution receipt, there's one and only one invalid fraud proof. Or sorry, one and one valid fraud proof. And these fraud proofs can be verified by the farmers. So they allow for stateless validation, and the farmers will come to consensus themselves over whether this fraud proof is correct, and then they will include it in the chain. They will basically reorg this chain of execution receipts that the executors are producing. There's an assumption here that there is at least one honest full node. Doesn't have to be a staked executor. It can just be one honest full node on the network. Of course, it's not under some kind of attack like an Eclipse attack. And this seems to be a pretty reasonable assumption for any kind of decentralized network. And again, the point of this decoupled execution, the reason it's designed the way it is to get away from this farmer's dilemma. So we don't want the farmers to have to maintain the state, but we need somebody to maintain the state. But we want to make sure that they can't lie about that state. We also want to minimize the amount of computation that farmers are doing as well. Basically, we're trying to make running a farmer, make it so there's almost no economies of scale for running a farmer, so that as many people run the farmer as possible. We can have as decentralized of a network as possible. We can have as much participation, as much storage on the network as possible. And we don't wind up with some kind of pooling or some sort of centralization of the protocol. Okay, and then how to compare this to some other protocols. So we have this idea in computer science of lazy versus eager evaluation or execution. And this is a really good way to think about this. So Ethereum sort of standard coupled model is basically eager execution, where the blocks are executed as soon as they are seen. On the other side, we have something called lazy execution. So there's a paper called Lazy Ledger. The blockchain's named Celestia that kind of exemplifies this. So they have no execution whatsoever. So it's never executed, at least not on the layer 1 level. Clients can execute it client side, almost like a layer 2 approach to execution. But there's no sort of global state. There's no consensus or no interoperability between these contracts, at least not natively. And this is also sort of the way that Arweave works. Arweave has its own smart contract layer called SmartWeave. It's basically the same idea as Celestia. So these are sort of two extremes, and we fall basically in the middle. So we are eager, we're initially lazy, but eventually eager. So another way to think about that is the farmers are lazy. They don't evaluate the execution, but the executors are eager. And as soon as the farmers produce a block, the executors evaluate it. But we have a way for the farmers and the executors to sort of come to agreement over what the valid execution is that's very efficient for the farmers. So this is actually very similar to the way that Flow Network works, kind of in principle. We've tried to make it simpler. Flow is a very complicated network. If you think what we're doing is complicated, take a look at what they're doing. And they're also working in the BFT consensus model. So proof of stake, 2/3 honest majority assumption. We're trying to make it work in the Nakamoto consensus model. A really good analogy is actually Optimism or Optimistic Ethereum, the L2. They have these really, really long fraud proof times, these really, really long settlement times. And that's because they have to basically compete with all other transactions on Ethereum to get a fraud proof in. And you could do this sort of liveness attack or denial attack to prevent the fraud proofs from getting into chain. In our case, since we have this sort of native to our blockchain, we're able to make this very, very efficient. So we would expect, if there's one honest node on the network within like two propagation delays, so like 2 to 4 seconds, we would expect to see a fraud proof. And certainly within at least the K blocks that we would normally expect for the confirmation latency of a block, we would expect to see a fraud proof. So it's very, very fast in our case. Okay, let me pause again if there's any more questions from the group, or maybe it looks like there's some questions in the chat here. And Nazar's answering them, great.
Yeah, I'd like to add here that the fact that we can decouple execution from the consensus also means that the amount of execution that executors are doing can actually be larger than in a regular network, because farmers can still continue producing blocks. They are not waiting for the execution to finish. Execution is kind of happening in like parallel to the consensus, to the safety. And that basically means we can make executors so busy that they will be running execution 100% of the time. So it's not like in regular blockchain where you are doing some execution, then you are propagating the block, you are waiting for others to import it, and then they can build on top. those things can kind of happen all the time in parallel. And that allows to achieve what is called vertical scalability, where you have one blockchain, but you're running more stuff on it thanks to this decoupling.
Yeah, great point, Nazar. Thanks for bringing that up. Yeah, Nazar's actually writing an article on this. He's been giving a presentation at the WASM conference next month or later this month about that. So be on the lookout for a great Medium article that really deep dives into this. Okay, if there's no other questions, we'll move on to the next section here. All right, so now let's talk about the storage layer. This is where a lot of the utility that we're working on right now comes in. So this is how do we make sure that the data is persistent essentially forever, or as long as the blockchain is in existence. So the first problem we have to solve is to make sure that the history of Subspace, the blockchain itself, is actually persistent forever. And we want to do this under the scenario where the history of the blockchain could be much larger than what any one particular node or what particular farmer could store locally on their disk. So for example, if the blockchain history was 10 terabytes and you only had a few hundred gigabytes, or we assume that the average farmer only had a few hundred gigabytes, we want to make sure that the system still works, that it's still consistent. That it has its integrity. And so that's the first problem here. So there's several aspects to this. We want to make sure that nothing ever gets deleted, nothing's ever erased from the network. We want to make sure that the different parts of the network, like one block is kind of, a block at the very beginning of the network has about the same redundancy as a block at the end of the network, or an old block is about as redundant as a new block. So that's load balancing. We want to make sure that it's retrievable, that it's addressable, so that we can always go fetch some old block, some old transaction. We can know exactly where it is and we can go get it very quickly. We want to make sure that we can sync as well, that we can sync the whole history from Genesis, that we could do a light client sync, that we could do a full node sync, that we could just sync our plot. We want to be able to do a very efficient synchronization, kind of in the same way that BitTorrent does like very efficient fetching of movies from a decentralized network. Like that's kind of the model that we're trying to achieve here. So to do this, we really just use some honestly pretty standard computer science distributed systems tricks here. So to make sure that the data doesn't get erased, we do an erasure coding. So we basically expand the data using this mathematical formula that ensures that as long as we have a constant number of parts or a constant fraction of the data, we can always reconstruct it. So in our case, if we had 4 here, we could reconstruct it, 4 original pieces and 8 pieces after the erasure coding. We could reconstruct it with any 4. And then we scatter those pieces across the network. So this circle here is like a ring that is the domain of the hash function that we're using for consistent hashing. So every piece gets hashed. We actually hash the index of the piece. So kind of as the sort of the piece number as it appears in the history, we hash that index and that maps it to the ring. And this results in this sort of load balancing. So this is sort of similar to the tags and the solution range. It's just a different area that we're talking about here. And the farmers, they also have these identities that are linked to their plots, and they map these identities, they hash these identities to the ring as well. And we have something like a nearest neighbor policy where the farmers are incentivized to store the pieces that are actually closer to their node identity. So we get this sort of natural load balancing in the protocol. And then we can leverage this. We can construct a DHT or a distributed hash table, which is kind of a structured peer-to-peer network on top of this, but we can make it very, very lightweight. So again, this is kind of how BitTorrent works. It has this DHT, but in BitTorrent, all of the data is kind of addressed on the DHT. This is also how IPFS works. Actually, all of the objects in IPFS are kind of addressed on the DHT or like cached on the DHT. In our case, we don't need to cache all of the pieces. We just need to cache the farmer IDs or the node IDs because we know that if we want a particular piece, that if we just find a farmer ID who has a close node ID to the piece ID, then we can always retrieve the piece. So it actually is a very, very lightweight, very efficient DHT, which is beautiful because it sort of scales very gracefully, even with millions and millions of farmers. And even if we had trillions of pieces on the network, it doesn't really affect the overhead of the DHT very much. And on top of this, we can construct a super light client. So this is based on Fly client, which is an approach where instead of having to sync every block header in the chain, you only have to sync a logarithmic number of block headers. So that means a few megabytes worth of data, and you can basically sync from Genesis all the way to the tip of the chain and be assured that you are on the longest chain. When we combine that with our fraud-proof scheme, we can actually be assured that we're even that we know what the correct state is for that longest tip of the chain as well. Okay, so this is our storage pricing model. So this is solving the problem of making sure that we don't end up with more history than we have space available on the network. Or basically, if we were to add up all the plots of all the farmers, all the space pledged on the network, we want to make sure that it never exceeds, or it never gets to be smaller than the actual size of the blockchain. Because then we would start losing data, right? Even with all this fancy stuff we're doing, we would basically start losing data. So we want to incentivize this. We want to provide incentives to make sure that this situation never actually occurs. And the solution to this is to have a dynamic cost of storage, or that means in Ethereum speak, that would be like a dynamic cost of call data, or in Bitcoin, that would be like a dynamic cost of OP return, of what is the cost per byte of putting data on the chain. In pretty much all other blockchains, this is constant. In our chain, it changes. It changes every block, and it changes based on this formula, which says if we were to take all of the coins that are in circulation, and we were to divide that by the space available on the network, and the space available is really just all of the space pledged, which we can get from the solution range. We can know with high accuracy how much storage is on the network without having to go out and count drives. And then if we take away from that the space reserved, the size of the blockchain, we have this delta left over. And that delta basically says, for this much space that's available, you'd have to use all of the coins on the network to buy that space. And you couldn't even buy that all in one block if you wanted to, because there's bandwidth limitations and how much data you can put in a single block. So you'd have to do this gradually over many blocks. And as you did so, the cost of storage would increase exponentially. It would basically approach infinity, or the full coin supply. Now, as this is happening, so as we're approaching sort of the capacity of the network, the cost of this storage is being put into the fee, and this fee is being passed on to the farmers. So it's basically becoming more profitable to run a farmer at this point. As it becomes more profitable, we would expect more farmers to come on the network, or existing farmers to pledge more space. And then this value here will go up, the space pledge will go up, the delta will get larger, the cost of storage will go back down. So we have this sort of feedback mechanism to adjust the cost of storage based on supply and demand effectively. So a good way to think about that is a two-sided marketplace. And we like to think of Subspace as one aspect of Subspace is this sort of two-sided marketplace for storage. You have a supply side. This is the farmers pledging space to the network. You have a demand side. This is applications that are reserving space on the network. If you were to compare this to some other protocols, something like Chia only has a notion of supply. There's no utility. There's no demand. If you were to look at something like Arweave, it only has a notion of demand. It doesn't have a notion of supply, because it's not proof of capacity consensus. It's proof of work consensus at the end of the day. We sort of have both. And so there's another protocol that does that. That's Filecoin. And but they're doing it in a different sense. So going back to your question earlier, Chris, they are providing this temporary storage. So it looks more like Amazon S3, where you're paying by the month or you're paying by the quarter. It has this fairly complex pricing mechanism where you have to basically go onto this off-chain decentralized exchange, find some miners. They don't call them farmers, they call them miners, to agree to store your data. And then you have to basically wrap this agreement or this SLA into a smart contract, post it to the chain. And then once it's posted to the chain, the consensus basically audits these contracts, and that's how Filecoin block production works. In our case, we've tried to make this much simpler. And you can think of it like an automated market maker, like Uniswap, for example, where there's just these two pools. There's the supply pool and there's the demand pool. And we're trying to achieve some equilibrium based on the amount of credits that we have on the network. And this all just kind of happens naturally. It's just incentives versus like structure or process around this. Anything you want to add to that, Azar?
Yeah, first of all, this is like very important that the cost of storage on Subspace is not really tied directly to the cost of the Subspace credit, which is of course like a cryptocurrency. It is actually tied to the real world cost of storage, because as soon as there is an imbalance, there will be an incentive for farmers to join the network and fix that imbalance, or for users to come and like reserve more space because it's cheap, right? So in the end, even if there is a fluctuation of the coin, in the end, it will average out to the actual real world like cost of 1 gigabyte of the hard drive on the market, which is important. And also there was a question from Andy about execution versus storage on Subspace. The fact that we have this storage is like an artifact of the fact that we try to solve the fundamental problem of the blockchain scalability. And once we can achieve scalability, it just naturally happens to be affordable to store data on chain versus off chain, just like a side effect of that solution. It wasn't like the goal to build a storage blockchain and then like have this all nice features on top of it. It was like the other way around.
Yeah, great point, Azar. Any other questions from the group?
Your webpage, or perhaps one of your earlier slides, said that you're working on, you have these various blockchains that you're storing. I'm curious, is that part of your, just like you're internally funding that storage, or how is, who is, I mean, there's supposedly some payment being made for this. I'm curious who is paying that in this case?
Yeah, that's a great question. Yeah, so right now on our testnet, there are no storage fees. So it doesn't cost anything to put storage on our network right now. Whenever we go live with mainnet, we're planning to have endowments from several different foundations to fund to subsidize this blockchain storage that we're like what we're doing right now with Polkadot and Kusama. But most projects, most developers would just be purchasing their own coins and using those to pay the cost of storage for their dApps.
Yeah, there was a question also a while back about Ethereum archival nodes. So it would be possible to archive the whole Ethereum on Subspace, and then if you want to start a new full node and you want to sync from Genesis, Subspace will be one of the sources where you can actually get all of the history instead of relying on some other voluntary archival nodes on Ethereum providing that feature for you. Because on Subspace, it will be incentivized by the protocol itself, so you'll be ensured that the history of Ethereum will be available forever with the same guarantees as other data on the blockchain.
Okay, we've got the question about content policing in here from Andy. Okay, so our philosophy is that censorship resistance is a feature and not a bug, and we are really big believers in keeping this protocol as permissionless and open as possible. So there's nothing to stop someone from uploading illicit content to Bitcoin or Ethereum or using it for illicit purposes, that's really the way that a blockchain should operate. Now, if the community decides that they would like to have some sort of content filtering policy, or if somebody would like to build an implementation that does that, or that's a proposal that the community comes up with that gets put into like an SIP, which is our improvement process, then we would do that. But we're not planning to build in any kind of censorship mechanisms in the blockchain right now.
Hey, Jeremiah, I have a question about your feedback or your control system that you got illustrated here. So I guess it feels like it's a little bit hidden here, but it feels like there's got to be somehow, or even if it's implicit, there's a target replication factor. Is that correct? Or, I mean,
yes.
And what is that?
For simplicity here, we just put it as 1. But basically, you can multiply the space pledged, the space reserved by the replication factor, by the desired replication factor here. and you can achieve the same thing. That's an open question that we haven't determined yet of what the desired replication factor is. It probably realistically can be quite low, like less than 10, especially with erasure coding. If you look at most other block distributed storage networks, it tends to be about 2 or 3. Like in Filecoin, I believe 3 is the default replication factor. But in all honesty, we expect it's going to be very, very high for quite a while. If you look at like Chia, they had at their high point about 60 exabytes of storage on their network. We think we're going to break that. I think we're going to be 100 plus exabytes of storage on our network. And even if we had 1 exabyte of useful storage, which is like ungodly amount of decentralized storage, maybe like 100 petabytes is even a lot. We'd still be looking at like a 1000x replication factor there. So we think it's going to be quite high for quite a while, to be honest.
Yeah. Okay, I'm slow. I think I'm slightly confused by you saying that your target is 1. I mean, earlier you're talking about these erasure codes, so it seemed like you wanted to have, like, if you're going to store, say, any data. My impression was that you wanted to have it, erasure coded, which is implying. I mean, if you're doing any erasure coding, the implication is that it's a replication factor of more than 1. In my understanding of what an erasure code is, the whole point is that you can handle something being deleted. So I guess I was just slightly confused by that. I haven't, anyway, it feels like,
okay,
if you're going to do any storage, I mean, if you have any erasure coding, then you're having, maybe I don't understand what you mean by replication factor.
Yeah, and I'm sorry if I misspoke. I was just saying we use 1 as an example here for explanatory purposes, but it will probably be like 10 or higher, as the actual replication factor that we're going to try to achieve, as the minimum. And then if you add erasure coding on top of that, it's probably, it's even higher. It's not even linear in the erasure coding, so you might actually achieve. So that's like 10 over the erasure coded data, not over the original data. So like 20, sort of in the naive case, with like 2x replication. But there's actually a formula you can look at with sort of the scattering that we have, the erasure coding and the replication factor, and you put all those together, and you can calculate like how many 9s of reliability you have. And we're still sort of parameterizing that to know exactly what we want to achieve, but it's gonna be pretty high. Nazar, maybe you could touch on that.
Yeah, I was sorry, I was typing the answer in the chat, so I missed that.
Oh, we were just talking about the replication factor and the erasure coding and the desired replication factor.
Yeah, so right now on the network we have erasure coding that produces as much parity shards as data shards. So basically we expand the history in 2x, and that space reserved is already accounting for that. So like 2x is 1 basically replication factor. But if you want to increase reliability, we will apply replication just naturally, just to make sure that nothing is deleted. But we are also considering to increase that erasure coding factor itself to something like 4 or 8 or 16. It just has some implementation challenges which we are trying to resolve right now. But the basic idea is to ensure that history is never deleted. And depending on how network behaves, we will adjust that parameter with the runtime upgrades, which Substrate framework allows us to do. So basically, the community can decide what the replication factor should be to ensure that everything that is stored on the blockchain forever is actually stored forever.
Thanks, Cesar. Okay, great. So let's move on to talk about the application layer and what we can do, what kind of interesting stuff we can do for Ethereum with Subspace. So to start out, let's talk about the storage API and the developer SDK that we're using right now, or really anybody can use to interact with Subspace, called Subspace.js. So this is really a very simple API. There's two methods, put and get. So basically you can write data to the network and you can read data back from the network. And we treat data just as these abstract objects. Just, it could be a record, it could be a file, it just can be any kind of abstract data. It's sort of opaque to the protocol, what it is. the object will get put into a transaction. So it'll basically get wrapped into a transaction. We have a special transaction, which is basically like a call data transaction in Ethereum. And this transaction will be gossiped up, to the farmers. The farmers will include it in a block. The block will then make it into the history. It'll get archived into the plots. It will be addressable within the DHT. And then if you ever want to get the object back out, you just call it by its ID, which is just the hash of the object. So it's content addressed. And then you can basically retrieve, the object is sliced into pieces, okay, just like we have the pieces of our blockchain. These objects become part of the blockchain and get sliced into these pieces. So you retrieve these pieces and you reconstruct the object, and you can just hash the reconstruction to verify that it actually is the object that you wanted. Okay, so we're using this right now to archive the .sama ecosystem in its entirety. And this is kind of a really high level overview of how this works. So we've got Polkadot on the top, Subspace on the bottom. So Polkadot, of course, has a relay chain like the Ethereum beacon chain, and it has all these parachains, which are like the shards of Ethereum. And we're literally taking every single block of the relay chain and all the parachains. We're wrapping those blocks in these storage transactions that we showed you here. And we're publishing those to our network. They're getting included in our blockchain, and they are stored on our testnet, and they're retrievable. We actually have an application we built called the Relayer that shows this, that's live on our website. This has gotten a lot of interest in the .sama ecosystem, and we're actually working on an integration with the Rococo testnet. So this is going to become the default way to sync a node on the Rococo testnet, and eventually, hopefully, for the entire ecosystem. We're doing this for both Polkadot and Kusama. And we've designed this in such a way that it's very modular and extensible, and it can really be done for any kind of blockchain, anything that is abstractly a blockchain. So it can be done for Ethereum, it can be done for Cosmos, it can be done for Solana, Bitcoin, and we have a roadmap to eventually do that for all of the different chains, all of the different ecosystems. So when we look at Ethereum, of course, there's a lot going on. There's a lot happening. It's an exciting time to be in Ethereum. But there's a lot of data that's being generated. And the question is, where is this data going to live? So of course, we have the Ethereum main chain. There was the question earlier about, can we run an archival node or a full node of Ethereum? The answer is yes, the same way that we're doing it with .sama. We can do that with Ethereum. There are rollups that are using the call data on Ethereum. Some of them are using the call data on Ethereum. Some of them are not. Some of them are storing it on a centralized server. Some of them are storing it on a decentralized network. This is something that Subspace can be used for. There's the beacon chain now. There's soon going to be many shard chains. The question is, who's going to run archival nodes for all these shard chains? It's already quite a burden to run an archival node just of the main chain. And then, of course, there's all of these DApps that have all of this off-chain data. There's some, data they have to put on chain. There's a lot of data that they're not putting on chain. Going back to Jeff's point earlier, that maybe should be stored off-chain, maybe should be permanent and decentralized, like the blockchain itself. Like if you have an NFT, right, you would want that NFT image or the file associated with the NFT to have the same persistence as the actual ownership data. Or else it kind of becomes worthless at some point. This is something which is on our roadmap. We're actually getting ready to start implementing this, the ability to archive at least the Ethereum main chain and some of the rollups, some of the L2s as well. And just to sort of recap what some of the benefits are here that there can be for Ethereum. First off, we have the ability to sort of scale without being concerned about bloat. So this is this problem of like, well, how big should the block be? We don't want it to get too big because then it's more burdensome to run an archival node, to run a full node, and Subspace really just provides this release valve so that this history and even some of the state, which there's this whole problem with like state rent that's been discussed on Ethereum. How can you archive that state? How can you resurrect that state? That's something that Subspace can be used for too, as sort of a secondary storage mechanism for that. Of course, we get much better decentralization. We don't have to rely on traditional centralized infrastructure to run archival nodes, to sync nodes. We can do this in a decentralized network. kind of back to the original goals here. And we can also take all of this data that we're archiving, and we can use it as the foundation for a bridge if we validate the data. And this is actually something that we're just starting to do in Polkadot and Kusama, is we are validating the consensus of the finality gadget of Grandpa for the data that we're bringing in. So we know we're not just storing some data which could be the history of .sama, but we actually are storing the valid canonical history of .sama. And this is basically one half of a bridge. We're actually planning to eventually have a parachain, which will be the other half of the bridge on .sama. But we want to do this bridging with other chains. We want to really do it with all chains eventually. This allows us to know if we have this validated data, we can have this common API for querying all of this valid blockchain history, sort of a cross-chain decentralized API for the blockchain history, maybe for the blockchain state as well. We can also use these bridges as a way to do cross-chain messaging and to move state and to move history and to offload this stuff across chains. So we again, we really see ourselves as a protocol for other protocols. We're really trying to integrate with other blockchains, help make them more scalable, more decentralized, more secure, more interoperable, and really provide the sort of infrastructure layer for the whole crypto and Web3 ecosystem. All right, well, thank you very much. I appreciate everyone's time.